Hi everyone, I am Pravalika. My new ID is TN567. In this video, I am going to explain about fuzzy matching and trees. While coming to fuzzy matching is nothing but a technique which we use to find the approximate matches between strings, which are accounting for typos as well as variations. Here in fuzzy matching, we determine the minimum edits needed to match the strings. While coming to exact matching, we use the exact matching when we need the strings to be identical in every possible way. Here we use direct comparison and exact matching. While coming to the differences between fuzzy and exact matching, fuzzy matching is known for handling the variations between the strings. It does not require the complete agreement which is required in exact matching. While coming to the use cases, fuzzy matching is known for handling misspellings and data inconsistency, while exact matching is only known for retrieving the precise data. While coming to the algorithms, fuzzy matching uses complex algorithms like Levenstein distance, uh, while exact matching uses simpler methods like direct comparison between strings. While coming to performance, fuzzy matching is computationally intensive when compared to exact matching. Exact matching is generally faster and more efficient. Also, fuzzy matching is used in search engines and the information retrieval system to enhance the user experience by providing the relevant results even with the imperfect queries given by the user. Uh, Also, exact matching is used in database lookups or when verifying the passwords. So these are the differences between fuzzy matching and exact matching. While coming to the similarities between Needleman-Wunsch and Smith-Waterman algorithm, we can say that both the algorithms use dynamic programming techniques to make sure of optimal alignment by evaluating all the possible alignments. We can also say that both algorithms handle affine gap penalties, which also allows different scores for gap openings and extensions. We can also say that the both algorithms can be customized with the different scoring matches. Um, for instance, we use Blossom and Map scoring matrices to suit various types of sequence or alignment needs. So while coming to the differences between Smith-Waterman and Needleman-Wunsch algorithm, we can say that Needleman-Wunsch algorithm performs a global alignment, which aligns the entire length of the sequences, while Smith-Waterman algorithm performs local alignment, which also focus on most similar regions within the sequence, which is different from the Needleman-Wunsch algorithm. While coming to handling of n gaps, Needleman-Wunsch algorithm penalizes gaps at the ends to ensure alignment across the entire sequences, whereas Needleman once lead to suboptimal alignments, while Smith-Waterman does not penalize gaps at the end, focuses solely on the best matching segment. While coming to the computational complexity, Smith-Waterman algorithm is more computationally intensive due to its focus on local alignment, while uh, Needleman-Wunsch also computationally intensive, but its complexity is generally lower when compared to Smith-Waterman algorithm. While handling large data sets, it performs global alignment. Also, Needleman-Wunsch algorithm provides a single optimal global alignment for the entire length of the sequences, while Needleman-Wunsch algorithm produces multiple local alignments within the sequence. So these are the similarities and differences between both Needleman-Wunsch and Smith-Waterman algorithm. While coming to the heuristics used by BLAST algorithm to speed up the process of search. BLAST algorithm is nothing but basic local alignment search tool, where we use different heuristics to find the local similarity between the sequences. BLAST algorithm uses word matchings, where we break the queries into small subsequences called words. It also searches for exact matches in the database. BLAST algorithm also uses high scoring segment pairs, where we extend word matches to find the high scoring alignments. BLAST algorithm also uses a threshold to disregard the low scoring matches. E-values is also one of the heuristics used in BLAST algorithm, where we filter out statistically insignificant matches. Gapped alignment is also one of the heuristic used. It also adds a gap to improve alignment. We also use a two-hit method in BLAST algorithm, where we look for two close matches before extinction. We also use a database indexing, where we create indices for fastening the search process. Also, we avoid repetitive regions to focus on significant matches by filtering and masking the low complexity regions. We also use parallel processing in BLAST. It also utilizes multiple processes to speed up the process of search. So these are the heuristics which we used in BLAST algorithm to speed up the process of search for sequence similarities. While coming to the level order traversal algorithm, uh, level order traversal algorithm is a traversal method where we visit all the nodes level by level from left to right. While coming to steps involved, firstly, we start by creating an empty queue. This queue will manage all the nodes at each level of the tree. Next, we enqueue the root node of the binary tree into the queue, which is also known as a starting point of a traversal. Next, if the queue is not empty, we dequeue the node. We dequeue the current node and we are processing, and then we process the dequeue node. For instance, we print the value of the dequeue node, and then we enqueue the children. And firstly, we enqueue the left child of the dequeued node. Since we visit the nodes level by level from left to right in level order traversal, and then we enqueue the right child of the dequeued node if it exists, and then we repeat the above process until the queue is empty, making sure all the nodes are visited level by level. So this is the example for binary tree, which I have used for level order traversal. Here the root node is 1. Firstly, we enqueue the root node 1. So we queue the value of a root node, which is 1, into our queue. Next, at first level, we dequeue the node 1 and process it, where we display the value of a dequeued node, which is 1, and then we enqueue the children of 1. Here we can see that the children of 1 are 2 and 3. So we queue 2 and 3 into our queue. Next we go to the second level. Here we dequeue 2 and display the dequeued node, which is 2, and then we enqueue the children of 2, which are 4 and 5. So next we have 3, 4, 5 in our queue. Next we dequeue the first element in our queue, which is 3, and then display the dequeued element, which is 3, and then we enqueue the children of 3, which are 6 and 7. So now our queue has 4, 5, 6, 7 nodes in it. Next we move to the third level. Firstly we dequeue 4 and process the value of 4. Next we in our queue we have elements 5, 6, 7. Next we dequeue the node 5 and display its value. After dequeuing 5, we have 6 and 7 in our queue. Next we are gonna dequeue 6 and display its value. Next we are going to display the dequeue the last node which is present in our queue, which is 7, and then display its output. So after dequeuing 7, our queue is gonna be empty. So in first in level order traversal, here we visited the node levels. Here we visited all the nodes level by level from left to right. So while coming to analyzing the time complexity and space complexity of level order traversal, we can say that the time complexity of level order traversal is big O of n, where n is nothing but number of nodes which are present in the tree. While coming to space complexity, big O of W is the typical space complexity, where W is the maximum width of the tree. In worst case, for a complete binary tree, maximum width is at the last level, which is going to be 2 power h, where h is the height of the tree. But for general trees, maximum width is smaller than 2 power h. So this is the example binary tree. Here the root node is 1 and the height of the binary tree is 4, since it has 4 levels. Here for time complexity, the tree has 15 nodes. During level order traversal, each node in the tree is visited once. So time complexity is a big O of n. So time complexity for this tree gonna be big O of 15, where n is the number of nodes present in the tree. Since there are 15 nodes, it's gonna time complexity gonna be big O of 15. While coming to space complexity, the maximum width of the tree occurs at the last level. This is a complete binary tree. The last level has 8 nodes. So the space complexity is big O of W, which is nothing but big O of 8, where 8 is the width of the tree at last level. So in summary, we can say that the time complexity of a level order traversal algorithm is big O of n at worst case, and space complexity is gonna be big O of W at the worst case scenarios. Thank you for giving me this opportunity.